Well, good morning, Francis Heritage from Faculty. Faculty is the UK's largest independent AI company. We're 300 people. That's our sales pitch complete. And our thesis is that since 2010, the world now has 50 times more data. Businesses, organisations, public sector. Are we making decisions that are 50 times better in quality? We would argue not. And so we've decided the thing that's missing is understanding about your data. And the reason for the presentation today really is to demonstrate the framework we're using to explain our computational twin, and which is something you may find useful as a handrail when you're talking to your sort of stakeholders about why investment in your digital twin projects might be useful. So our product, is called Frontier. It's a computational twin of complex systems in which people make decisions. So it's designed to make those decisions more transparent, make the impact of those decisions clearer, particularly the second or third impact of those decisions as they cascade through a complex system, and allow you to do scenario planning in a much more transparent and accurate way, and also help you to predict how your system will react at any given time. We're predominantly using it in hospitals at the moment, but as we go through the presentation, I'll talk through how any system can really use this. I'll firstly talk through the OODA loop constructs that we use: observe, orient, decide, and act, although we've changed orient to understand. My background in the military, and anyone with a military background knows the OODA loop decision-making framework, and we've used that as a handrail to which we explain how Frontier works. I'll then talk you through how Frontier is designed. We won't look at the code, but I'll talk you through how our sort of nodes and event firing system works, and how that allows you to build very complex understanding of the second and third impacts of decisions you make, and how the scenario planning system works. But again, I can take questions on Slido. So 50 times more data, not 50 times better decisions. When you make a decision, you observe something, you understand what you've observed, you decide what you're going to do, and then you act. And we would argue current planning software, ERP software, only gives you a bit of observe, maybe time late, and only a bit of understanding, but it can't give you root cause analysis, let you scenario plan, or understand the best thing to do in a complex system. And so our product Frontier uses machine learning models at each of these areas to give you that. So how does it work? We build a computational twin of your decision-making framework. We connect to the data that you've got, and then we provide decision features on top of that. So what I now focus on is the element on the right. So this is a computational twin of an A&E department, and we've built these for some NHS trusts. So if you use a systems thinking model, you can think of an A&E department as patients arriving. You decide whether or not to admit them. You assess what you're going to do with them, assess what beds they then go into within the hospital when you get them out of A&E. You discharge them, hopefully, and then they get safely discharged either back home or back into somewhere else that's a primary care node, for them to recuperate potentially somewhere else. Sounds simple, but actually this is happening a lot of times every day, and the second and third order effect of making a wrong decision can be quite catastrophic. And so those elements in purple are where we built machine learning models using external variables, and the element in blue, the rules of the hospital, are hard coded. So those things don't change. So if we walk through the journey of a patient, the patient arrives, well, our model can hopefully predict in advance who's going to walk through the door, and we use external variables about the environment like temperature, previous admissions, the nature of the population that your trust is in, including age and gender, things around amount of COVID currently in your environment from 111 calls, potentially in the future from wastewater. And hopefully we can give you some confidence about what you're going to face that day and prepare your A&E department for what you're actually going to face, rather than those knee-jerk reactions. Somebody then arrives, we take information from that patient, and we can start to predict, again, using a machine learning model, predominantly Bayesian hierarchical modeling, what their length of stay is going to be. How old are they? Is it a cardiac issue? Is it a broken bone? Has this person arrived or presented with these sorts of things before? And do we know historically how long it's taken to get that person through and discharged? And now you can start to understand, if you can do that for every patient, how the system overall could be refined to get the throughput of patients through as most efficiently as possible. So each of these nodes is a Python class. The Python class has essentially two elements to it. It has a state So admissions, for example, we tell you how many people are waiting in admissions, and it has an event firer. So as soon as something happens, the admissions node will fire to the assessment node to say, I've just moved this patient from me to you. And the machine learning model for length of stay can then start doing its work as well. The other element that's involved is the variables involved in each of those nodes that we know about. So in admissions, it could be something like the mean assessment time, how sick people are, the probability that somebody is fit. And so all of those things combine together to give you an understanding of what that patient looks like in code, essentially. And you can create twins for any process where there's an input, a process, and an output, and lots of decisions in between. All of these involve people, but they don't have to. You can involve raw materials for a factory. And what we would do at the start of any engagement is to build the decision-making model that you already have and turn it into code. And like I say, you've then got the options to do all these various things with that computational twin that you've built. And I'll take you through a couple here. So forecasting, you can predict what's going to happen next. Rather than knee-jerk reactions that might actually cause a negative effect for your system, you can get ahead of that knee-jerk reaction and make the decision early. Here, for example, this is going to forecast what's going to happen to an A&E department that day, based on those variables I talked about at the start of the environment. Or scenario planning. You know, how many times has your boss come to you and said, I need to know what's going to happen if we do this and this and this? Here, for example, you can try to understand what would happen if you bring in another consultant to do some work. Clearly, that would reduce the variable defined as mean assessment time. That's only in one node, but as that node's impact fires to all the other nodes, you can understand how bringing in one doctor maybe at that decision point will affect everything else, and you can understand where the optimal place to bring that person would be. And so we found this OODA loop construct as a really useful way of framing the discussions that we're having. And so an apology for the terminology. Clearly, this isn't really a computational twin. It's more of a sort of digital model in that it doesn't feed into a physical system or a physical bit of equipment yet, but that might be coming. And the other interesting thing is we all take OODA loop decisions every day in our lives. So for a hospital, for example, anybody could use this for the particular decision they make. So the hospital manager could use it. If you've got a transformation/change manager, they can understand where to make decisions more effectively. If you've got a patient discharge manager or a primary care nurse or the person who's monitoring who's coming in, they can use this structure to improve their decision making. So our argument is by bringing all of these decisions into one place, firstly making them transparent, which you may not have, but secondly bringing in that layer of machine learning understanding, you can make decisions that aren't knee-jerk and potentially cause cascading negative effects throughout the system. You can get ahead of your decision loop and actually make better decisions thanks to that predictive analytics that machine learning could provide you. And we found that OODA loop to be a really, really useful construct when we're explaining what a digital twin is and improve decision making. Thank you.